and Jianfeng was a student of Neil Braun at Penn State, working on luminous quasars. And then he came here as a postdoc, working primarily for a couple of years with Peter Jonker, who's in the Netherlands presently at Space Research, whatever, SRAN, I think most of you have heard of it. And he's also been working with me, so working with both of us the last 3 years, and going to the University of Michigan to work with Elena Gallo in the fall, in September. So he's been working with me on this study of this X-ray binary Nova Muscae 1991, which had just one outburst so far, a very luminous outburst in 1991, very well studied black hole X-ray binary. And the objective that he's been working toward over a period of 2 years is to measure the mass of the black hole, which ultimately we'll use in addition to the distance and the inclination to get the spin of the black hole. So this is what he's going to talk about.
Thank you, Jeff. Jeff has virtually outlined this project. Yes, so I'm going to present the detail of this project here. And special thanks to Jeff and all the great collaborators. So it's a dynamical study of the black hole X-ray binary Nova Muscae 1991 with the goal of measuring its mass. Part of the work has been published, and the other part is in progress. So, why do we want to know the mass of the black hole? Well, actually, we want to know the mass of everything, but particularly mass is important for black hole because mass is the fundamental parameter of astrophysical black hole. Based on the no-hair theorem, mass and spin, the two parameters together provide a complete description of astrophysical black hole. And if you want to measure the spin with continuous fitting method, mass is the prerequisite. And to date, there are 24 stellar mass black hole identified, confirmed in the X-ray binary system. And here is illustration for 21 of them. So some of the X-ray black binary are persistent X-ray system. The majority of them are transient systems. We identify them only after the X-ray outburst. And our object here, Nova Muscae, also called this GRS 1124, is this one. It looks like the other about 9 systems. They are short period systems with a period less than 12 hours. Okay, so for this about 2,000 systems, we have mass measurement for about a reliable mass measurement for about 10 of them. And one remarkable feature of the mass distribution for this system is the mass gap. So here's a figure from the work of Zell et al. So for a presumed mass distribution with the minimum mass cutoff, the minimum mass cutoff is at this range, about 6 solar mass, which is far from the theoretical expectation about 2 mass. So there is a gap in this region, lack of 2 to 5 mass solar mass black holes. And if this mass gap is not caused by selection effect and other things, then this can provide constraints to the models of supernovae and gamma ray bursts to produce these black holes. And regarding the spin, so measuring the black hole spin via the continuous fitting method is basically measuring the radius of the innermost stable circular orbit, R-ISCO, for the system. So this is done by modeling the X-ray spectrum and with knowing the distance inclination with the accretion disk model, Novakov solar model. And this gives the relation between the R-ISCO and the spin of the black hole, shown here. Obviously, you need to know the mass of the black hole to determine the spin, the dimensionless parameter, spin parameter of the black hole. And the spin is very important for a variety of astrophysical topics. And one important example is the jet spin relation. So the group by Ramesh, Jeff, and Jack and work shown here found a positive correlation between the black hole spin and the jet power for these systems, supporting the Bradford dynamic mechanism to that the jet is powered by the rotational energy of the black hole. However, for this relation, we need a full population of the stellar mass black holes, and so far we have 5 systems here, and only one of them is a short period system, is A0620 here, and anchor the relation. So we need more short period systems. So here comes our object here, the X-ray node Muscae 1981. And Jeff already mentioned this. It has so far only one outburst in 1981. It's when it's discovered by these 2 satellites independently. And shortly after the discovery, it's dynamically established as a black hole binary, which in this work, and I will explain this parameter later. And more importantly, it's a short period system with the 10.4 hour period. And the system is actually transient, and it's a black hole accreting the secondary via the Roche lobe and form an accretion disk. Okay, so to marry the mass of black hole, based on this equation, this is basically the Kepler's third law. And so the mass of black hole is here, the big M. And what you need to know is the FM, the mass function, which is derived with the period system and the semi-amplitude of the radial velocity curve for the secondary. And this is obtained via spectroscopy. And you also know the mass ratio, the ratio between the mass of secondary and the black hole. This is also obtained via the spectroscopy. And you also need to know the inclination angle of the system, which is obtained mainly, in most of the cases, if there is no jet available, and you have to obtain the inclination by modeling the light curve from the secondary star. So this is done with photometry. And this has turned out to be the most challenging part for the short period system, black hole binaries, because the disk weighting issue. Disk weighting means that the light curve you obtain is strongly contaminated by the disk light. It's not the pure secondary emission, and the fraction of the disk emission could be high and varying. So, because of these 2 reasons, it's very difficult to model the light curve itself and to get the inclination angle. There are previous works on the inclination of this system and various results, but none of them have properly corrected for the disk weighting issue. And there is a spin measurement, Morningstar et al. Based on the result of this work, Jianfeng et al. And they obtain a retrograde spin. The spin is minus 0.25. This is pretty remarkable because based on the work of Tassos and Jeff, and the spin of black hole is mainly acquired via the accretion of materials. So it's very difficult to explain how the black hole has a retrograde spin relative to the accretion disk. So in order to tackle these challenges, we have adopted this approach. It's the simultaneous spectroscopy and the photometry. So we have the high resolution initial spectroscopy obtained by Magellan MAGE. We have 72 spectra of this system covering the full optical cycle, and we have additional spectrum for 38 standard stars. And in addition, we have the strictly simultaneous photometry, less than 1 second time difference, obtained by the 100-inch DuPont telescope at the same site, Las Camanas Observatory. So this is the first such simultaneous time-resolved observations on this system. Okay, so I mentioned the 3 elements for measuring the mass of the black hole: the mass function, the mass ratio, and the inclination. So now I'll discuss them one by one. First, mass function. As I said, mass function is obtained via spectroscopy. So this is shown the MAGE spectra of normal Muscae in 6 central orders, covering basically the visible light band. So you can see the remarkable feature, the broad and double-peaked Balmer lines, H alpha, H beta, H gamma, H delta, which is the signature of the accretion disk. And you also see some interstellar features surrounding the dust band. And actually, it also shows numerous absorption features here, although not very clear in this figure. They are the photospheric lines from the secondary, and these are the lines where we obtained the radial velocity of the secondary star. So the radial velocity is obtained by cross-correlate the object spectrum to the spectral template of the standard stars, and to get the relative velocity shift between the object spectrum and the templates, using the technique developed by Terry and Davis, very widely used technique. And so we have 38 standard star templates. So we need to choose the best templates which match the object spectrum. So the Terry and Davis give a R value to quantify the quality of the correlation. The R value is basically the height of the peak of correlation compared to the noise. So higher the Terry-Davis R value, TDR value means better cross correlation. So we did the cross correlation between the spectrum to all 38 stars, and we picked the one generated the highest TDR as our best fit template. So and this star has a color corresponding to about like 4,400 Kelvin effective temperature. The spectral type is around like K5. So for our best order of the spectrum, all the 72 object spectrum can generate the reliable radial velocity, which is plotted here, all 72 data points covering a full orbital phase. And we also get this radial velocity curve for other orders, 9 to 14, and for some of them, we can also use all or most of the 72 spectrum, but for some others, we can only use some of them. And so for this radial velocity curve, we fit them with the sinusoidal model shown here. So from the fitting of the radial velocity curve, you can get the semi-amplitude of the curve, the systemic velocity, and the time at the zero phase. And so these are results we get from multiple orders, and then we get a weighted average from all these orders. So the K2 velocity is about 407 kilometers per second. So based on this number, we obtain the mass function, which is 3.2 plus minus 0.06 solar mass, which is entirely consistent with the previous work overall set off, but we have a 3 times better precision, mainly because the high quality spectrum. Okay, second one, mass ratio. So these systems, these Roche lobe field systems, are considered to be tidal locked. So the rotational velocity of the secondary star is related to the mass ratio of the system, and also the radial velocity of the secondary star via this equation. So we already get K2, and if we can measure the rotational velocity of the secondary star, V sun I, or actually the projected rotational velocity, V sun I, then we can derive the mass ratio Q using this equation. And this is also done with the spectral we have got. And meantime, with the spectrum, we can measure the discriminating factor, which I just mentioned. So So this Fs is the total flux of the system, and this template represents the flux from the secondary star. At times of factor F is the stellar fraction. So the total light minus the stellar contribution to the disk flux. So the disk weighting factor, the disk fraction is just 1 minus F. So the V sun I and F are obtained simultaneously with the technique called optimal subtraction. So we have chosen the best template, which is this one shown here. And you can see the numerous photospheric absorption features here. And you can also see those features in the spectrum of Muscae shown here. And the absorption feature here is already broadened. The actual feature in the template itself is much narrower. So you broaden this feature to some velocity to match the width of these lines, and then you times the factor F I just shown. So and then subtract it from all this spectrum, and you got the residual. In ideal case, if you get the best match template and the best V sun I velocity and best the fraction, the residual spectrum should be a constant, except that this emission feature and this interstellar feature is constant. So for doing this, we have a set of the trial values of the velocity V sun I, and also a set of values of the F, and we tried these different combinations and find the residual spectrum which is closest to a constant, which is done by a chi-square test. It means to have the minimum chi-square. So here's the chi-square plot. We tried the different residual velocity from 0 to 150, and for each one we get a chi-square value. So you can see the chi-square curve here. And for each minimum chi-square, we got a value of V sun I. This is the measure of V sun I for this order, and shown here. And this histogram shows the error uncertainty of this this V sun I obtained by Monte Carlo simulation. And again, get average among these 6 orders. We got the V sun I is number 85 billion per second, and it's corresponding to the mass ratio between the secondary star and the black hole is about 0.097. And in the meantime, we got the disk weighting, also shown here for the 6 orders. And so we did this by using the average magic spectrum in each order. We measure the disk weighting. You can see here a dotted line. And we also did the same process for each individual object. So it's a histogram showing for the result for the individual object. And the dashed line is the average of the histogram. So using the 2 methods, we got consistent results. So it's prove the consistency of our work. So this is the first robust disk weighting measurement for Muscae with multiple multiple order Echelle spectrum. And we also find a trend of the fraction of disk light with the wavelengths. It's the fraction of disk light decreases when going to redder wavelengths, shown here. Let's see about this way. Here. Yes. So at bluer wavelengths, the disk fraction is high. At the red wavelengths, this fraction is low. So the previous work by Jianfeng et al., they studied the near-infrared light curve, and they ignored the disk fraction. Because our finding here, it looks like the disk fraction is even lower at near-infrared. Well, but it's not necessarily the case. As I can show here with a kind of toy model of the spectral energy distribution for this system. So we used black body, the 4400 Kelvin black body, to represent the emission from the secondary standard emission. And this blue square here are the disk emission derived from this disk fraction measurements. So these six points represent 6 orders. And we fit this with the power law model. And this magenta line is the combination of these two. So if we extrapolate this to longer wavelengths, with the longer wavelengths, the disk fraction decrease, but after a certain wavelength, because the black body falls more rapidly than the power law, the disk fraction actually go up. And this is also supported by the work by Reynolds as well. They measure the near infrared. The disk fraction and near infrared for this system is around like 50%. So disk rating is still important, no matter whether you use the optical light curve or the near infrared light curve. And now we use our result on the disk fraction to tackle the inclination. So for the ideal cases, if there is no disk type contamination, the light curve of the secondary star will show this kind of ellipsoidal modulation with two equal maxima when the configuration is like this, and both disk and the star is like this way. And when the star is rotating to this way, which means the disk is between the observer and the star, you will see the deeper minimum here. And when the star going this way, in between the observer and the disk, you will see the shallower minimum. So this system, the GRJ 1655, shown the ideal case of the ellipsoidal modulation. So people have good constraints on the inclination for this system. And then let's see the light curve we obtained. Okay. It's a simultaneous light curve with this magic spectrum obtained by DuPont. And here are the 72 points and phase folded. And here are the beam light curves shown here. Well, you can see some sort of modulation, but actually you don't see this ideal ellipsoidal modulation that is completely kind of consumed by this flickering. So we cannot use this light curve to modeling the inclination. And are we stuck here? Well, not really. So first, let's investigate why the light curve of the black hole binary, especially the transient system, can have this kind of behavior. Actually, for these ideal cases, it's very rare, and most of the black hole transient, the light curve is kind of like this way. And so the work by Control et al. Investigate a rich data set of the prototype soft actually transient A0620. They discovered that although the system is remain in active quiescence, but they have different optical state, means passive state and the active state. And loop is kind of in between these two major states. So in passive state, you see the curve is much better, much closer to the pure ellipsoidal modulation, and means there is little discontinuation here. But for the active state, you see a much more erratic light curve, and the system is brighter here in active state, which means which could mean there are higher discontinuation. So the system is higher and it's not ideal ellipsoidal modulation. And the Control's work and also the Quadra's work conclude that only the light curves in this passive state are suitable for the inclination modeling. If you use the active state, then you can have the very big uncertainties caused by this behavior of light curve. And now we see the Muscae in 2009 when we obtained our light curve. And we found it is brighter. So this system is monitored by the SMART telescope since 2003. And you can see the photometric data here. And this black square is our DuPont photometry in 2009. And from both the V-band and I-band photometry data, you can see a clear trend of the brightening over the years. In the V-band, it's brightened at a rate of like 0.04 magnitude, and I-band is 0.02 magnitude per year. Although the number looks small, but considering this multi-year time scale, it's actually very significant. So with this data, we found the first direct evidence of the brightening of black hole soft active transit while it remains in active quiescence. So what does this mean? This means, so this kind of brightening is predicted by the theoretical model on disk instability for this life cycle of the black hole soft active transit. So you can see here these different parameters: this accretion rate, the V-band magnitude, the disk, the radius of the outer radius of the disk, and the mass of the disk. This is just from the theoretical model. This is not observation. So the life cycle, this system are identified in outburst, and gradually going back to quiescence. So the brightness dropped significantly, and then the disk, the accretion disk, builds steadily via the accretion. In this process, the system got more and more brighter, and it goes into the active state. And until at some point the disk surface density reaches a critical point, it triggers an outburst and a new life cycle begins. So this means that the passive state is at the system just back into the quiescence from the outburst. And these curves are the best light curve for modeling the inclination. So for this system, it went outburst in 1991, and fortunately we got the light curve in 1992, right after it back in quiescence, in the I band, shown here, and B plus V band, shown here. These light curves had been presented in Oro's et al.'s work. So we use these light curves to model the inclination of the system, and we also adopt this 2001 J-band light curve, which looks good, close to the infrared modulation, to also include this in our modeling. However, we don't have the simultaneous spectroscopic observation for these light curves, so we don't have the direct measurement of the disk fraction for these light curves. Here comes again our 2009 light photometry. It's still useful, and we can derive the disk fraction for this light curve from the disk fraction of our 2009 photometry under the assumption of the emission from the secondary star remain unchanged, which is kind of reasonable because we don't expect that the secondary star itself has big change in the brightness. So the difference of the magnitude is mainly caused by the increasing of the disk emission. So now Muscae in 1982, the V-band magnitude is 20.5, and in 2009 is 19.05. So the difference is about 0.66 magnitude, which is actually a big difference. In over the 17 years, and the brightening rate over the 17 years is this number, which is entirely consistent with this brightening rate we got from the SMARTS data. So which means from 1982 to now, 2015, in this span of 23 years, these systems steadily brighten up at kind of nearly linear rate, about 0.04 magnitude per year. And in 2009, the V-band disk weighting is this number we obtained from spectroscopy. And combined with this difference in magnitude, we got the disk fraction in 992 curve in V-band is about 20%. Okay, so with this disk fraction constraint, we use the eclipsing light curve code, ELC code, to model a light curve. Here is one example. So this code can model the steady emission from the secondary star. And also a kind of steady pedestal disk emission is baseline flux from the disk. And also the variable component of disk, presumably from the hot spot at the outer region of the disk. So this work hasn't been finalized yet, and we're also working on the spin of this system. So I'm not able to say the results of the inclination and mass here, but I can show an example of the light curve, our model light curve. And you see, using this ELC code, we can model this light curve very well with this, with all these three components. Okay, now is the summary of the whole talk. So we performed the first simultaneous time-resolved spectroscopy and photometry of the system known Muscae 1991. And from the spectroscopy, we obtained the radial velocity curve and the mass function with the 3 times better precision than previous work. And we got the first measurement of the rotation broadening, the V-sun-I, and the mass ratio with this multi-order spectrum. And more importantly, we constrained the disk emission fraction from the spectrum. And we found the first direct evidence of the near linear brightening of the known Muscae over the 23 years, ever since it came back to quiescence from outburst. And based on this result, we selected passive state light curves to modeling the inclination, and we have constrained the disk weighting factor for these passive light curves, although we don't have simultaneous spectroscopy for these light curves. And with this result, we can further constrain the inclination and the mass of the whole system. So please stay tuned. Thank you very much.
Any questions for Jianfeng?
You mentioned that in the I band, the rate of increase was different from the V band.
Yeah.
What do you think is the difference to
Well, I don't see the. So I think it's related to the kind of spectral random distribution of the disk itself. If the disk emission, we expect the majority of them is at lower wavelengths. I mean, in the absolute way, like shown here, the majority of the emission is here, and you might expect its brightening is larger in the V band, but I'm not completely sure about this. I think with the disk instability model, maybe one can reproduce this difference between V band and I band, but I'm not very sure.
And in this curve, there is a point which is quite deep.
Yeah, this is here.
Lower of 0.5.
Yes, and this is a kind of outlier here, and you can also see from this figure. The point is actually this this panel here, and if it's this ideal relation, and this line should be between this and this line, but it's not. It's just an outlier, and for fitting the power law, we exclude this point here.
Okay, I'll ask one question then. So you see this brightening in quiescence in the source nova Muscae. Do you
Yeah.
expect to see that in other sources? Should we start looking for variability?
Yes, I mean, from this theoretical model, and we should expect this for, I mean, this brightening exists generally for all or most of the black hole subset transit system. And now we have the first clear evidence for this system, and there are some kind of evidence for like 80620. Like here, you see this brighter, the active state, and many points of active state actually, this point are after this point. So it's kind of, but it's not as clear evidence as here.
This is just one state, right? Quiescence state.
Yeah, quite.
And so you're just not comparing the states together, but you're looking at the variability of that one state over time.
Yeah, because for this system and the most of their lifetime are in the quiescent state, and outburst is only a very short time scale.
Okay.
After outburst, it comes back to quiescent and stay very long in quiescent state. Maybe Muscae has been 24 years, okay, even longer. And actually, this theoretical model can reproduce this long time span in quiescent state, I think up to even like 180 years using the ADAF and also the disk radiation models. So,
Okay.
So you mentioned the spin measurement for retrograde spin that was using the continuum fitting method. So I don't remember if you actually mentioned at the end the parameters that you get, the mass and the inclination, are they very different from the ones that we're assuming that work? Will this change the actual spin measurement?
Well, it's not finalized yet, but we do see the trend is like after probably including the contribution from the disk, and the trend is the inclination becomes lower and the mass of the black hole becomes higher, and this could make the spin change from retrograde to prograde. So
You could be more definite. No, I mean, in fact, it does make the inclination significantly lower,
yes,
and the mass significantly higher, and it does go to prograde
So
spin.
it pushes the spin to prograde.
yeah.
Cool.
I mean, we don't want to signal everything to other people who write papers very fast, but we can say that.
I guess you had a question, Jeff.
No, that was it.
Oh, okay. All right. Any other questions? Okay, if we don't have any questions, let's thank Jianfeng Wu. See you next week.
Yeah, I mean,
Thank you.
when I practice, I use the 45 minutes, but in this case, I just spoke much faster, so I'll use 60 minutes.
Happens to me all the time.
Oh, thank you.
You guys just observe these clusters for a while. Luxury.
Yeah, that's true.
Yeah, and so, we'll see your secondary is constant. So, you can get this, because you can subtract.
Oh, I forgot to tell you.